Let's use calculus now to compute the surface area of a sphere. We're working now on a three-dimensional problem, so it's going to be a bit more challenging. The sphere has the equation x squared plus y squared plus z squared equals r squared. So the strategy here is to draw a ring at a fixed height z here, and with an infinitesimal thickness given by ds. We're going to calculate what is the infinitesimal surface area of this ring, and then use the integral to sum over all of those infinitesimal surface areas to obtain the surface area of the sphere. So to determine what is the infinitesimal surface area of the ring, we need to first know the radius of the ring. So what is the radius of the ring? Well, the radius is just the square root of x squared plus y squared at fixed z. So the radius is the square root of x squared plus y squared, which here is the square root of r squared minus z squared. Once we have the radius of the ring, we can get the circumference of the ring. So the circumference of the ring then is 2 pi times the radius. So it's 2 pi times the square root of r squared minus z squared. So now we know the circumference of the ring. So the surface area of this ring then is the circumference times the thickness of the ring is ds. So the surface area is infinitesimal. I'll call it d capital S. The surface area then is the circumference, 2 pi root r squared minus z squared, times the thickness of the ring, which I'll call d little s. Okay? So that gives us our d capital S. And the solution of the problem will be to integrate this infinitesimal surface area. So to do that, we still need to know what ds is. So we can consider what ds is by considering first just the y equals 0. So we're just going to take y equals 0 and figure out what ds is. So ds is the same no matter what value of y we're at. So it's simpler just to consider being at y equals 0. So if we're at y equals 0, I can draw a triangle. So we have our ds. So the difficulty in computing ds is because it's along the surface of the sphere. So it's not in the z direction exactly, it's tilted in. So this is our ds, and the dz then is this vertical, and our dx is then this horizontal, and this is at y equals 0. So then we can use the Pythagorean theorem. So ds is equal to the square root of dz squared plus dx squared. And we can factor out a dz because we want to be integrating over dz. So that becomes the square root of 1 plus dx dz squared. And all of that multiplied then by our infinitesimal dz. Okay, now we have the problem of what is dx dz. We're at y equals 0. So we know that x squared plus z squared is equal to r squared. So we can solve this for x. So x is equal to r squared minus z squared square root. But in fact, we can have two values of x because x can be both positive on the front surface of the sphere and negative on the back surface. So we should put a plus or minus here for the two different possible values. In the end, it's not going to matter because I'm going to have a dx dz squared, so that plus and minus sign will get squared away. So now we should take the derivative here. So we have a dx dz. This is the square root of r squared plus z squared, so r squared minus z squared. So it's r squared minus z squared to the 1/2 power. So to take the derivative, you bring down a 1/2, and it becomes r squared minus z squared to the minus 1/2 power. Then you use the chain rule. So you take the derivative of the inside, which is minus 2z. So the plus or minus will become minus plus, and then we'll have a z. The 1/2 will cancel the 2, so then we'll have a divided by the square root of r squared minus z squared. And that's our dx dz. So then we can compute ds. So ds is this thing squared. So we end up with our ds here is the square root of this squared. So it's the square root of 1 plus z squared over r squared minus z squared, all times dz. Okay, let's continue over here. So what is this? Can we simplify? Well, we can turn this 1 into an r squared minus z squared over r squared minus z squared. So we see the numerator will have an r squared minus z squared plus z squared, which will become an r squared. So that gives us our ds then will be the square root of r squared, which is r, divided by the square root of that denominator, divided by the square root of r squared minus z squared, and that whole thing times dz. So this is the formula then for the infinitesimal thickness of our ring. So we have this extra factor of r over square root of r squared minus z squared multiplying the dz. That factor is very important because the square root actually cancels the square root in our d capital S, which is the surface area. That's 2 pi times the square root of r squared minus z squared times d little s. D little s is r over the square root of r squared minus z squared dz. So this then simply becomes 2 pi r dz. Okay? And that's the infinitesimal surface area of this ring. So the surface area of the sphere is equal to the integral over the infinitesimal surface areas. We can integrate from z equals 0 to capital R and multiply by 2. So that becomes 2 times the integral from 0 to r of 2 pi r dz. So that becomes 4 pi r times the integral of dz. The integral of dz is just z. So that becomes 4 pi r times r, or we get our formula 4 pi r squared for the surface area. Okay? A lot of work to get the surface area of a sphere is 4 pi r squared. You probably never did this before and just learned that this was the surface area. So let me summarize. We computed the surface area of the sphere using calculus. The approach was to draw a ring at a fixed height z on the sphere with an infinitesimal thickness ds, and then find what is the infinitesimal surface area of this ring, and then use the integral to sum over all the infinitesimal surface areas of rings from z equals 0 to r. The difficulty here was determining the thickness of the ring ds, and we had to do a bit of mathematics in order to get that. Once we got the thickness, then the infinitesimal surface area of the ring is just the circumference times ds, and that turns out to be a rather simple expression which is easily integrated to get the surface area equals 4 pi r squared. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video.